the free energy looks
So
different.
question A, so do we need to draw the genetic form of that in the UT plane?
Yeah, I'll just say, the free energy looks like this here, looks like this here.
So we divide the section again.
Yeah.
So you don't like to keep up the energy?
Pardon?
You don't like to keep up the energy?
Depends how bored you are. Depends how much time you have on your hands. Yeah, basically just this type of thing. Cool? Okay, we're calculating the correlation function. The two-point correlation function may be the most important object that we study in field theories. In our case, we're using it to define the correlation length. And what we're doing right now is a mean field calculation. And the equation we derived last time I'll just write a couple steps down. So we started from the second derivative of the free energy. With respect to two sort of fictitious on-site fields. And they're just introduced because, again, they couple directly to the order parameter. So we showed that this is equal to the derivative of the mean field magnetization on site, MI. And from that we derived something like where that is our hyperbolic tangent mean field expression for the magnetization. I just call it big M. And I replaced this first derivative here with the two-point correlation function. So let me pull out that temperature. There's a T there, so it's 1 over T. Okay, and I'm just writing it like this because we're going to calculate this in two limits, like we've done for other quantities in mean field theory. And one is above the transition, where the mean field magnetization is 0. And then what you'll do on your next assignment is repeat like everything I'm doing today, except with this term non-zero. Okay, so that's for T below TC. So I think your second question on homework 2, which I'll bring Friday, will be related to what I'm doing today in class. So today, let's calculate the mean field two-point correlation function above TC. Okay, so that simplifies that expression. So I do the easy things in class. You get to do the hard things on your assignment. Okay, so let's start. T greater than TC. The mean field two-point correlation function. So that's that thing I wrote up there. Lj. Okay, so I just want to factor out, the correlation functions occurring twice in there. So let's factor that out. And just be a bit careful when you're dealing with, this basically matrix algebra. Okay, so what I actually want is to factor this out. I have a sum here, so I can use a delta function and write a sum over both terms. Okay, so this term I'll write delta. This is ij. So if I have a sum over L, I can write it like this: JIL. And then this one is LJ. Okay, so I've summed over my L, so the only indices that should be left are I's and J's. Okay, so I've just factored out that 2-point function there. So this is the equation we have to solve, in this case when the magnetization is 0. And so we're going to do this using Fourier space. So it pays to be comfortable with these lattice Fourier transforms in any of these condensed matter calculations. Okay, so let's just, you've probably seen this before, but let's go through the Fourier transform relatively carefully. So let's introduce a lattice Fourier transform. Okay, so I can imagine having a field, which I called phi, right? Which again is you can imagine it as being the, fluctuating value that the average value, say, that the spins take as a function of space and time. So that field undergoes a Fourier transform in a momentum space like this, where I've defined phi k is that field and momentum. And everything's simplified when we assume periodic boundary conditions. Which for our purposes means that the field, if you've translated by the lattice linear size, then the field returns to its original configuration. So let me define that field. Phi I is phi I at this position vector r. And if I translate through the system by the linear size, L, so L by L by L by L hypercube, and that should be in some direction, the same in some direction lambda, I'll use for a unit vector, then that field should be equal to its value before that translation. So L is the linear size of the system, and lambda is the unit vector. along the primitive lattice, whatever you want to call it, the basis directions, lattice directions. Okay? So, right, so because of this periodicity, then e to the I, what do I got? K dot R plus L lambda which gives us the, if you will, the discretization of the momentum space of the Brouillon zone, where the lattice unit is just 2 pi over L, and n is some integer. Okay, so it's basically defining your lattice in K space, where, I mean, remember, in position space, your R vector is a sum over all those unit vector directions. And I'll introduce A here. And A is going to be the lattice constant in real space. Right? Meaning A is the distance between 2 points, 2 neighboring points, an angstrom, whatever that is, whatever the lattice is. And L is, in this case, the integers in real space. So as you know, or as you should know, because of this, because of the periodicity essentially, you know, you have a lattice that only has a finite number of lattice points. What you do is you define a Brouillon zone, or you define K space that is discretized with the same number of lattice points. Okay? And essentially in the same way that the lattice is periodic in real space, you know, you can restrict your analysis in K space to just the first Brouillon zone. So it means that this thing here since K lambda plus 2 pi n over A doesn't change. Say K dot R. I don't know, maybe there's a easier way to say that, but okay, so if you haven't yet mastered these, lattice Fourier transforms, because doing the analysis of some Fourier space is basically how you solve most of these problems in condensed matter. Okay, so we've defined the Fourier transform of the field. We need the Fourier transform of the objects here. Okay, so we're just going to take the Fourier transform. And there's a strategy to how you do this. You take the Fourier transform of everything, and then you equate you know, you'll have a bunch of sums, say, over momentum space, and you're going to equate objects inside those sums. So going forward with that strategy, so we basically just have to we have to define the Fourier transform of all those objects in that equation. Okay. Well, so delta's known, so let's do G and J. Okay, so I'm going to, I don't know why, but I changed from K to Q, and now I'm going to stick with it. Otherwise, I'll forget farther down. So Q is just K here. So I need to define this G and Q space, which is the object that I'm actually going to solve for. So it's the analogy to this field transformation, except I have, you know, a 2-point function, right? So I have two lattice vectors, Ri and Rj, say. Okay, so I have like sum over Q, and I'll define that 2-point correlation function in momentum space as G of Q. And I'm going to write it like this, Ri minus Rj. And when I write it like that, I've explicitly used translational invariance. Implies or assumes so again, another physical ingredient that's going into this is the idea that, you know, if I have a distance between, you know, if I have an Ri and an Rj, then this 2-point correlation function only depends on the distance between them. And if I translate this somewhere else on the lattice, then I can treat that object as being the same once it's translated. Okay, so we're starting to build in symmetry. So translational invariance gives us this form. It's the same for J, right? This is like your interaction matrix. So if you ever have a system that breaks translational invariance, maybe you want to put disorder in your system. So if you have quench disorder, which means that maybe a field at site I is different than the field at site J. So once you start doing stuff like that, breaking translational invariance, then this whole analysis breaks down. So this is really just the simplest case. N's the number of lattice points, if I didn't define it already. So this is just the same exactly. I'm just defining the object J. Okay, so now I'm just going to substitute these expressions into my equation. And I have a delta to worry about there. So I don't know which one I like better. Let's do the second last one, actually. Okay, it's going to take a while, so I'll switch boards. Okay, so that first Gij, minus 1 over t. Okay, so we've got a sum over L. So this is a term that you're going to have to worry about. So I have two objects, J and G. I need the Fourier transform of both of them. So I need two momentums, momenta. Let me label them with different labels just to be safe. So I'll do Q prime and Q double prime. And we'll see how many of these unique labels matter. When in doubt, give everything a unique label when you're doing Fourier transforms. And then look how things shake out at the end. Because if you make a wrong assumption that two of these momenta are equal, then you'll basically screw up. So I got J Q. Let's do prime for J. Q. E to the I. Q prime. That's going to be R. I minus RL, say. Or RL minus RI. Then I need G of Q and e to the IQ dot my labels L and J. Is this right? Yeah, there's two Fourier transforms. What else? I think that's right. Oh, yeah, right. Right here. And right here. Okay, and on the right-hand side, I just have the delta function. So that's the left-hand side. Equals the delta function, which is just the empty Fourier transform. I'll just use Q. J. Okay, so here I've used, let's make a note of it. I've used the definition of the delta function, which is basically the only trick that is used in solving these expressions in Q space. And similarly, you can use the delta function also in Q space. So I'll call it Q. Well, I'm going to use it here. I'll call it Q prime, Q double prime. So the inverse transform, just need that minus sign there. So it'll be Q prime minus Q double prime. L, R, L. So I have two R's of the same index here. And that's what lets me use this delta function. And what that delta function does is constrain the Q's in these two sums. Okay? So it's as simple as that. So therefore, I'll just write everything out. I'm going to use one of my n's here, but I have one left. Okay, so when I use the delta function there, I'll have one n left, and let's just use Q, because now these are all separate sums, so. Yep. And then I'll have J and G. And then I should have the same e to the I q dot Ri minus Rj. And then just the delta function on the right-hand side. So right? Now what do? Just equate all the terms inside those sums. Okay, so it means this thing is equal to 1 over t, like this thing, right, is equal to 1. Make sense? Q. Okay, so let's see, 1 minus 1 over t JQ, right, just equals 1. So you might see this written sometimes. 1 over t is just beta. So G of Q, 1 over 1 minus beta JQ. And what we need to do is solve J of Q somehow. Okay, but this is the starting point. And this is the point where we're going to start making approximations, or more approximations, if that's possible. So remember, we're still in the mean field theory. We've still done the saddle point approximation. So we've approximated the functional integral just with the, the maximum of the argument, which means minimizing the action. That's what relates the free energy to that action functional, if you will, S of phi. So now we're going to introduce a concept of the long wavelength limit. So, when we're starting out at the lattice level, so before you do the Hubbard-Sturgeonovich transformation, this idea of a lattice, the lattice constant, right? This stuff is sort of what defines the short wavelength, the UV limit. The behavior we're interested in the 2-point correlation function, in order to define the correlation length, is in the long wavelength limit. Okay? So we want to study this J of Q somehow when the distance between I and J is great, is large. Okay? So we are making a connection between the microscopics of the system of the Ising model through the Hubbard-Sturgeonovich transformation, the introduction of fields. Okay, so that's our link to the microscopic. And now we're asking a macroscopic property. We're going to take this object, which was derived as the mean field approximation to that Hubbard-Sturgeonovich transformed functional, and we're going to take the long wavelength limit of this. And that should give us a macroscopic property. So we need, what is this, J of Q, where have I defined it? Well, we can define a body inverse. Jij, e to the minus here, iq ri minus rj. And like I said, we're interested in the correlation function at large distances. So we can define a range, I guess. So how would I do that? So let me say that Ri minus Rj, right? So the length of that vector is greater than some, of course, this is hard to define exactly. There's some UV length scale or some lattice length scale that's maybe related to that A, or it's related more accurately probably to the effective range of the interactions. Because when you define a Hamiltonian, you know, the lattice is mathematically effectively defined by the interactions, not necessarily by the lattice constant. So if you had first neighbor or nearest neighbor interactions only, then the effective range is just A. But you could also have interactions that are maybe first neighbor, second neighbor, third neighbor, which then means that, you know, the range of the interactions here is maybe larger than A. So that's the, you know, I'm just defining it in a vague way, but that's the range that you have to worry about. It's the range of the interactions. So for example, it could be approximately equal to A, but you know, not necessarily. So we're going to do a Taylor expansion of J of Q. Under this assumption. And the reason we can do that is because if we're interested in large distances, it means we're interested in small q. Small magnitude q. So we'll take that exponential or in the expression of J of Q there, then we'll expand that exponential in a Taylor series. So this type of approximation, again, is typical in, I think, these condensed matter problems. When we move on to doing the renormalization group, we'll do it, quantitatively, we'll do it in momentum space. And then we can define both small q and large q cutoffs of the integrals.
Question. Aren't we considering Ri minus Rj of order 1 over q? So like, isn't the product of q times the difference of r's?
Well, you have all q's.
Of order 1.
You have all possible q's. I mean, depending on all different length scales. And so we just want to ignore all the length scales below some massive length scale. So we only want to consider the Q's corresponding to that. You know, we're cutting off all the smaller length scales.
Right, but then what happens when you when your sum goes to I and j such that Ri minus Rj is of order 1 over q when it's really large, like across the whole lattice, because then you can't expand it.
When your distance is the size of the lattice, that's what you want. That's the case that you want, right?
Yeah, but then q times the difference of the r's is of order 1.
Where are you going to keep those terms? Okay, yeah, actually I know, I see what you're saying, yeah. There's like a paradox here, right? Because you're expanding, I want to expand in Q, but I need elements of the sum that are...
Yeah.
I don't know. Yeah.
Probably some reason why it's okay.
No, that's worth thinking about. Let me write the expansion, we'll look at that. Oh, just a question. Does this make sense? Okay, so let's do this Taylor expansion. So J of Q. So let's leave the sum Ij. Yeah, so it's the exponential. So what you're saying is, if this is small and this is large, how are you justified in doing this expansion?
I think it's okay because if you set Q to be small and then you want to choose the terms where Ri minus Rj is of order 1 over Q, then the product should be close to like 2 pi or some multiple of 2 pi, and then you can do it like modulo 2 pi and expand around 0. So I think it's fine.
Makes sense. It's like if your distance is the whole lattice, which, you know, if this distance is almost spanning the entire lattice, it's equivalent to saying that your distance is this, right?
Maybe to add is that the Jij should be pretty fast, right? Relatively fast. So for
that's a good point. Yeah.
For large Rij, the pretty fast.
Right. So then, if this range is small, then the Jij will cut that off. Yeah. I like that. I think that's a good explanation. Yeah. It means you made an assumption about this. So this is perfectly valid if you assume. So Jij is less than 1 for Ri minus Rj greater than R, say. Not the only sketchy assumption we'll make. Let's assume, what's it called? When the matrix is symmetric? Yeah. If the interactions are symmetric, then this term will go to 0. So that's also an assumption on Jij. So this is some sort of point group symmetry, I guess. It's a discrete symmetry if you reflect around, you know, the special points in the hypercube. Then the linear term disappears. So again, we're making assumptions about sort of the interactions, you know. They're not always valid, so you have to keep that in mind if you're doing a real calculation. So I think this will make sense. help us write J of Q. Okay, so that first term, I'm just going to call it J. The linear term, I'm going to call 0. So I'm going to have 1 over 2n. Squared. I've done this before. Defining Ji is just equal to J, big J, sum over all, too many J's, Jij. Okay. Okay, so let's look at that second term. So this is the thing we're going to have to evaluate. And let me go through it relatively quickly, and then we'll look at what symmetries we need to do simplifications. So what do I change? That dot product. Okay, I want to write it somehow like so I have different I'm in a d-dimensional hypercube. Oh, I've already defined the unit vectors, right? Lambda. The lambdas are the different directions. So let me just call it sum over all directions. And then that lattice difference in that direction. Okay, so this term is worth thinking about. So then, let's just look inside that sum. So Jij, well, let's look at the sum. Jij Q So I have two terms because it's squared. So let me just be careful and keep those indices separate again. So I'm labeling this with two different directions, lambda and lambda prime. Okay, let me talk about symmetry for a minute here. So those terms, okay, so you need to include in the sum, say, all the directions. So, you know, x, y, z, right? You got to cycle through all the labels there. I want to simplify this with a symmetry that gives sum over all directions, but just a single sum. Is that obvious? I've taken this double sum, and I've just written it like this. No, it's missing terms, right? Let's come back to this. It's missing cross terms. X, y, y, z, right? But let's come back to that for a minute. I'm just going to finish this rest of this calculation first. For d dimensions, I've just written a sum which I'll also go over. And let me just now get rid of all the non-Q dependents. This is what I wanted. I want an expression that has some Q dependence. And all I'm doing here, which I'm going to explain some more, is taking this term and pulling out Q squared. So let's call everything else some whatever, kappa. Something that has no Q dependence. I got an N, so 1 over ND. So again, you're summing up all the interactions. That's some other kind of effective range, if you will. You're summing up interactions times the distance, or the distance squared. So this should give us JQ, if I've done it right, J minus, I left that half out in front, big kappa, Q squared. But let me go back. I want to justify these steps here. Okay, if you can justify this, throwing away these cross terms, then you can write this like this, then you pull out that Q squared. Now Q squared is just going to go in here. So you already see we're getting to the... You'll recognize this as the propagator, right, for the Gaussian theory, if you've done field theory before. So that's all we're calculating is the propagator. But we have an interaction. In principle, it's microscopic. Jij is defining the interactions in the Hamiltonian. So let's just think about the symmetry that's required to get that step that I've labeled with a star there. Okay, so I want to start maybe with, so what I'm trying to do is prove those two lines. And I've done it in general dimensions. Yeah, okay. But let me take these two dimensions and just do it in these two labels over different directions, and just run the labels, say, in the two-dimensional plane, and we'll just visualize this. I'm just writing a thing on top there, Ri minus Rj, Ri minus Rj. Okay. So let's just take maybe X and Y. Okay, let's just write that thing out just in the two-dimensional plane. So we're just restricting ourselves to d equals 2. So all I'm just going to do is demonstrate basically the symmetry you need in order to make that step. So for 2 dimensions, I'm going to write out the right-hand side there. I'm getting lazy, but there's just 4 elements in the sum, right? So when both indices are equal to x, you'll get something like this. When both indices are equal to y, But you can have lambda equals x, lambda prime equals y, and vice versa. So you need cross terms. Something like that. So you get two of those things, it's the same. So what you need is basically those terms that go to 0. Or the sum of all those terms goes to 0. Say, for example, ij, x and y. We need this term to be 0, which means we have to make an assumption about this again. So imagine you have a lattice site I. You know, if your interaction is such that, for example, you define an arbitrary vector, which is your distance between I and j, right? So here's 1j. And you're performing a sum over all those different j's. And if you have a symmetry such that, so here's a j prime, so that'll be an element of your sum. That's a j prime, or double prime, say j triple prime. 1, 2, 3, 4. Those are all going to be elements of that sum. So you'll see that these terms here, call them delta, I don't know, delta Rx, delta Ry, have a sign associated with them. Right? So here they're both positive, delta Rx, delta Ry. Here one's negative. No, both are negative, one's negative, one's negative. So if you have the symmetry of the interaction such that the sign of those things matters and cancels all those different terms, then that'll be satisfied. And that's a very natural symmetry to have for the interaction. I believe it's just called inversion symmetry. Inversion usually means your vector, it's like if your R vector goes to minus R, but it's basically just one of these point group symmetries, C4V or something like that. Or maybe C just 4, I forget. So again, you need a certain interaction. You need a certain assumption on the interaction in order for this to be true, which is an important step in pulling out that Q squared. So once you have that, then your expression up top there. Okay, so let me just write this term, Jij, sum over lambda. I'm going back to general dimensions. Okay. All those terms, you know, you'll have xy, xz, yz, blah, 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 which generally just gives you the thing we want. That's the thing I wrote here, I guess. So then the next step, if I wanted to convince myself that I could write this in terms of this, I might just write this out in a couple dimensions too. So say lambda for x and y. Which means that this thing would just be x squared qx squared I don't know why this is interesting, but okay, you just do this yourself. Just start writing out all these terms and you'll see that that equals that. Equals. So I think the inversion symmetry is the important part here. In order to pull up that q squared, you need to assume inversion symmetry. And from that expression, you'll get this for the d-dimensional hypercube. So this isn't a proof. This is just a demonstration of that symmetry basically in 2 dimensions. Any questions? Does that make sense? So now we have this expression here. We're still using this to solve for this thing, right? The propagator, if you will, or the 2-point correlation function. And you think I'm going too slow with all these assumptions and stuff? Don't worry, you'll use all this on your assignments. So where am I? J of q. So then from that expression there, two-point correlation function momentum space. 1/2 kappa q squared. Let's see, I want to pull out a t on top, so j over t plus 1 over 2t q squared. I'm in the mean field, so I can use the fact that j is equal to tc here, right? That's only valid for the mean field approximation. Tc equals j. So let me pull a t out. Then we're going to have t minus tc plus 1/2 kappa q squared. That's something I derive every year in a different way, in a different class. It's the propagator for the Gaussian field theory, if you will. This is like your mass term in the field theory language. This is the term in the phenomenological Landau theory, the one we developed that couples to the field squared. So sometimes it's called a mass, or R sometimes in Landau theory. And you assume that that thing's proportional to t minus tc, so that the quadratic piece is the piece that, so you have a free energy that looks like this. Then the quadratic piece, there's also a phi-4 piece, U phi-4, is the piece that changes sign at the phase transition, which gives you this, right? So the coupling in front of the phi squared is somehow this piece here. And then the extra piece that gives you the correlation function in Q space is this Q squared dependence. Make sense? So we do, like I say, we do that over and over again many times. There's no correlation length in that thing, so I still haven't done what I wanted to do. What I want to do is define the correlation length. So what I need to do is take this and somehow get G in real space. So I've done a long wavelength limit approximation here, remember? This whole mess. So this is true in the long wavelength limit. So what does that mean for real space? That's a hard problem, actually, doing that inverse Fourier transform in d dimensions. You need some like Bessel's function of the second kind. That'll be on your assignment. So I can do it in 3 dimensions, because then I can use contour integration. So let me just do it in 3 dimensions. Okay. It's an important dimension. Why not? Okay, so in 3 dimensions, we can take, so we have a Q space we have a Q space expression, and what I'm going to do is Fourier transform it back into real space. But I'm not going to use the lattice Fourier transform. I'm just going to take the continuum limit. Okay? Because I'm in a long wavelength limit somehow. And so what I've essentially defined when I do that is a continuum theory. So the Fourier transform looks the same. All you do is replace the sums with the integrals. And you just got to be careful with the normalization of the volume in the sum, if you will. So let's just talk briefly about this. So the reciprocal lattice spacing is 2 pi over L. Reciprocal lattice spacing. Your momentum space, remember, is discretized. So that's 2 pi over L in every direction. Okay, so now you can define a volume, 2 pi over L, 2 pi over L, whatever. There's a volume of that unit cell in reciprocal space. So I'll call it okay, so in the continuum limit, that goes to 0. Right? You're shrinking that cell down to 0. But the total volume of the Brouillon zone, or the total volume of your sample, has to remain fixed. You're not shrinking your sample down to 0, right? I always forget how to do this, and this is what you remember. So you have reciprocal lattice spacing, defines a volume. The total volume has to be fixed, so that V naught, say in Q space, times the sum isn't equal to that integral, d over Q. So total volume, say V in 3D, it's just L cubed, say. What else? There's a density of states. It's volume over 2 pi cubed. I don't know if that matters. So I have lattice Fourier transforms. I have, every time I have a sum over Q, let's do 3D. So the sum over Q is just equal to, or just goes to the volume. Over 2 pi. Okay. So it's a reciprocal lattice spacing. That's just a V naught. And then the integral. So V naught dq. Anything else I have to know? There's an n, right? So there's a number of lattice points. So L cubed over n is just A cubed. I don't know if that matters. So that's how many lattice points you have. No, sorry, n is the number of lattice points you have. This is a length associated with it. This is just a number, right? So they're related by that lattice parameter A, the lattice constant. Okay. If that looks unfamiliar, brush up. So now I'm just going to take the continuum Fourier transform. So G of R, which is the thing I want. Do it in 3D. 2 pi G of Q, be the I Q dot R. Much nicer in the continuum. I can do this because I can do spherical polar coordinates in 3D. Phi, this isn't your field. I'll call it this type of phi. 0 to pi, this is theta. Jacobian sine theta. And let's see, my radius goes from 0 to infinity. And there's a q squared from the Jacobian and g. And then q dot r in these coordinates, q r cos theta. Okay, pretty standard stuff. So we need an integral IA cos x, let me call it sine that theta integral can be done with this. So then G of R and I pulled out the phi integral. What do I do now? I just put in G of Q, I guess. Just got to keep track of your Q's. I got to pull out those T's and everything too. Yeah, so I got a q on the bottom and a q squared up top. So I'm just going to leave it like that. So then it's sine QR dqqt t minus tc kappa q squared. All right, so this is the one I can do with a contour integral. It's got to complete the squares on that thing. So it's q minus I times something, right? And it's I times, you're going to have to take a square root of basically that mass term. So it's I 2 t minus tc over kappa. And plus and minus I root 2 t minus tc over kappa. Now, I'm almost set up to do a contour integral that they only know how to do with exponentials. So let me pull out that sign, turn that sign into an exponential. One over 2I, the IQ dot R minus IQR, they're scalars. This thing gets annoying to write really quick. I think I can do this now. I just pull this 2I out front. And then I have something that looks like a contour integral. So we can just use I feel like I need a Q out front in order to do this integral. Oh yeah, here it is. Yeah, okay, so this is good. So then, I'll do plus or minus I z squared plus square root of a squared. No, just a is plus or minus I pi e to the minus root a. That's what I used. So when you do that contour integral, now you get your expression that defines the correlation length. But this is only the expression for g of r in 3 dimensions, remember. Otherwise, you just need to do this integral more generally. That's where those Bessel functions come out. Okay, if I haven't dropped anything. R is on the outside of that thing. What's your correlation length? We did all this, so it took us like 2 days to get here. You remember what we're trying to do? Remember we have we have correlations. This is the 2-point correlation function. R is the distance between two sites, I and j, just defined with this R vector. Or now it's just a distance R, because everything's symmetric, in space. Inversion symmetry and blah, 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 translation. So we just have this vector telling us there's a distance. There's a correlation function that depends on the distance. It's exponentially decaying. Okay? And the thing that governs that decay is this. That's 1 over the correlation length. That's how you define it. So it's got to be this thing upside down. So that G of R proportional to, I don't know, e to the minus R over Z. And this is for D equals 3 only. So when you do the D-dimensional calculation, you're going to have to worry about the dimensional dependence of this expression, basically. But what you'll find, luckily, is that the argument of the exponential doesn't change. The only thing that changes is this piece here. So this is homework 2. In D dimensions, you'll find G of R. Again, R is just the distance, but now you're in higher dimensional space between the two sites. So it's going to go e to the minus R over psi. I'm not going to introduce. So it's going to be D minus 2 over 2. So I haven't. There's another exponent, the anomalous dimension, but I'll talk about it later. Yeah, so that was the point. We wanted to define the correlation length, and then we wanted to define a critical exponent nu. So what's new from this? The critical exponent that governs the divergence of the correlation length. It's a half. So your mean field value for nu is 1/2, because that's a square root.
So the exponent of the denominator is correct.
D minus 2 over 2. That's what you'll find on the assignment.
We sub 3 D.
Mm-hmm. Well, I was guessing, but now I'm wondering if this is D plus 1 for a field theory. Okay, check this. Assignment. Yeah, you're right. I think my definition of D might be off. Because if it was 4D, yeah, so it's D minus 1, I think, here. Because I'm thinking of the path integral. Then you would get 4 minus 2, which is 2 over 2 is 1, yeah. So that might be the wrong D. Anyway. Since I can't do simple subtraction, what else am I doing? Oh, I'm defining the correlation length exponent. This board sucks. Okay, so the correlation length exponent. The correlation length is the most important object in all of these analyses. It diverges at TC. Okay, so it looks like I don't know, something like this. And the dependence on T minus TC generally is like this, which defines the exponent nu. And everything we've done has been a mean field theory calculation. So nu is 1/2 within mean field theory. What else do you have to know? Well, the fact that this goes to infinity at the critical point is the source of the scale invariance of a critical system that we're going to use to derive the renormalization group. Okay, so even though the exponent maybe isn't perfect, you know, the behavior of this thing as you approach the critical point is right. I mean, it is diverging. Again, that's not true at a first order transition. Gives us scale invariance, gives us criticality at a continuous transition. This divergence does not happen at a first order transition. So first order transition isn't described by this theory. First order transitions just, you know, they have discontinuities, latent heats, hysteresis, coexistence. The free energy just looks different. This all comes from the fact that the free energy, you know, changes continuously as you go through the transition. Right, so criticality gives us rise to the scaling behavior. So next class, we're going to start looking at fluctuation corrections to mean field theory. But it's more demonstrative than, I guess, quantitative. The most important thing is this divergence. We'll talk about scale invariance. And, you know, the correlation length is just a good way of sort of anchoring or making your thoughts concrete about systems as they approach criticality. You know, it's basically the measure of length over which spins are correlated with probability 1. Right, so of the length. It's got a length, it's a length scale. I mean, e to the minus r over the correlation length, right? So if you do a dimensional analysis on the free energy, it has dimensions of length. It's the only length scale in the problem. And it's the measure of length by which, you know, two sites or two spins or two particles are correlated with probability 1. Or the same, or correlated with probability. Okay, so you've done it, you've derived the correlation length, learned to love it. We'll talk about it for the rest of the class. What we're going to do next time is, hey, this is still mean field theory. It's like 3 weeks it took us to get this to this point. There's another exponent that I talked about at the start of class called eta, which governs G of R right at criticality. But based on my inability to write down the correct functional form on the bottom there, let's save that for later. So we're going to define one more exponent. And the reason it's not falling out here is it just happens to be 0 in mean field theory. It's called the anomalous dimension. Ada will talk about it later. So we're going to move away from mean field theory now. Okay, so we're going to start to systematically put in fluctuations. And so what we want to do is we've assumed that we have like a free energy. We have a minima of the free energy. It's like the saddle point approximation. Our big M, that magnetization, is the value of the field or the spins, if you will, at that minimum. But now we want to put in like fluctuations around that minimum, right? So mean field theory, we're down here. And what we want to start thinking about is, if this starts fluctuating around that minimum, how do we deal with that? And how does that give us corrections in this formalism? We're all set up to do this because we have the functional integral. So all we have to do is basically take the action and expand the action in, small fluctuations. So delta phi, which is the magnitude of these things, okay? And so next time we're going to start looking at these fluctuations corrections to the mean field theory. And it takes a couple classes to sort of, again, hash all this out in detail. But as we're doing that, I want you guys to think about whether or not this makes sense, the way that we include fluctuations. And the moral of that next part of the lecture is that it's going to give us inconsistencies. So this is going to motivate the need for a different framework. This idea that fluctuations aren't captured properly by this theory. And that's going to lead into the scaling theory and the renormalization group. So we're going to go down some false road. I mean, it's going to be instructive, but it's not going to give us sort of the proper critical theory. And we're going to come back to this idea of the correlation length and then reevaluate this approach, this idea that we have criticality and scale invariance. And that'll take us through the last half of the class. So you guys owe me an assignment on Friday, and I'll have your homework too for you then. So bring your assignment to class. Question?
Yeah, so in order for the correlation line to be analytic at equal to TC, would that mean that kappa would change sign?
It's non-analytic. The non-analyticity, is that a word? And the free energy basically come from that. Remember I said that was part of the question is where does the non-analytic behavior of thermodynamic things like specific heat or whatever, susceptibilities, where does that come from? So the way I think you should think about this is it comes from that. It comes from the fact that that thing explodes at T equals TC. Kappa is just, where did I write it? It's just a sum over all these real space interactions. Those things are fixed. So that kappa is just, it's not it's a constant, but it's just some, feature of the interactions. So I'd say no, it doesn't change.
Okay, so what about the graph though? Would it still have that symmetric behavior?
Well, it's not necessarily symmetric. No. I mean, you can have different exponents actually on each side. I've done this. Oh, great question. I've only actually derived this side because I set my magnetization equals 0 to start a class, remember? So what you guys are going to do is derive this side on the assignment. Hey. And it's not symmetric. This, might have a different amplitude. It may have a different exponent, but generally you could have a different exponent. You could have plus or minus here. You'll have some, I forget what I call it out front. Maybe it's kappa here. Maybe I've abused kappa, I forget. But you have some number here that's also an amplitude, and that amplitude ratio doesn't have to be 1. So it can look different, yeah. So on your assignment, I'm going to have you do I'm going to have you do the right expression for this. I'm going to have you do this side of the calculation. And then I'm going to have you do, you basically, in your question 4, you're doing a phenomenological like Landau theory for the ON vector model. I'm going to have you derive essentially this from microscopics in the case of n equals 3, so 3D rotors, using Hubbard-Stratanovich. Okay. I'll have that ready for you Friday. All right. More questions? Lunchtime?